Okay, let's have a look at evaluating polar areas then. We're going to look at the sum of these areas. We're going to get this formula here. I'll go through it quite briefly. Let's take a little segmented area here. Can you see that there? We've gone from a point PRQ to a point Q, which is a little delta R along, and a little delta theta along. So we've gone along delta theta, this little angle in here, up to Q. And in so doing, we go along a distance delta R, don't we, from R that was here originally at P. So that's what we've got in terms of the picture then. So this slice of segment of areas we can label as delta A, small segment of area, and that will be given by using the sine rule, won't it? The area of this triangle is half AB, these two times together, which are here and here. A half of that, AB, sine of the included angle, which is delta theta. So there's our area then of delta A here. Now, we know the area of a segment between two limits will be the integral delta A between the bounds, won't it? And we'll get the total area. And we can then use a substitution change of variables and write the A d theta d theta and have bounds theta 1 and theta 2. So that will work fine. Oops. So that's what we've got then. If I can draw the integral correctly, there we go. So that's what we've got then. So what is the A d theta then? Well, here let's have a look at delta A delta theta to start with, and then take limits and let delta theta tend to 0 to get the A d theta. Well, we know that delta A is equal to this stuff on top, or here, we've just written it before. Divide by delta theta then. Now the key is, as delta theta tends to 0, delta R will tend to 0, because it's well behaved in this picture here. So as delta theta tends to 0, the Q tends to P and the delta R will tend to 0. That's fine. And then also the property of the sine is that sine delta theta tends to delta theta. Now why is that? Well, really, let's just draw a quick little picture of the sine curve and you'll see why that is. If I draw sine x, say, on the xy axis, and you can see what happens to the sine curve as it gets small. Can you see that the curve itself approaches, the line y equals x? It has gradient 1. So the sine of the value will equal the value, because it approaches this gradient 1. Because when you differentiate sine, you get cosine, and cosine 0 is 1. So it's of gradient 1, as we said. So sine x for small x equals the value x. So can you see that sine delta theta then, because delta theta is small, will equal delta theta. So this tends to none other than delta theta. So here this can be replaced by delta theta, and delta theta over delta theta is 1. Delta r tends to 0, so you're simply left with half r squared. So that's the A d theta then, in terms of the limit. So we can replace the A d theta by half, which we can put outside the integral, r squared d theta. So here's our formula then for the integral, working out areas. So in this section I've written a little widget as well, which actually puts in the half and calculates these areas, but all you need to do is tap in the function of r, and everything else is taken care of for you. So if you have problems of your own that you're working on, then by all means, of course, use the widget, and also you can check the solutions by that as well. Okay guys, all the best in this section then. I thought that would be good to do a little bit of bookwork just to get our heads around why we obtain this formula here. But in this section, we're simply going to use the simple integral formula to obtain the answers to the questions. Okay then guys, I'll catch you again. Cheers!